Okay, so last lecture we talked about what? The starting definition of a tree, right? And how to implement a tree on the code. Okay, so today we talk about the minimum spanning tree, which this tree is abstracted from a graph. Okay, so yeah. So first we discuss about the tree and the graph. What differences regarding for tree and the graph? Tree is first tree is undirectional graph. Okay, tree is part of graph actually, right? Yeah. So the graph maybe contains many trees, right? So we know it's many to many, right? So we define the tree first as a tree as a what? Undirectional graph. For example, this is a tree, right? But undirectional graph may not be the tree, right? May not be a tree. Okay. For example, this one. Is this a tree? It's not a tree because why? They have the what? One circle, right? One circle. Okay. So this is a not tree. All right. So tree must what? They do not have a circle, right? So on the tree. What about this one? Is this a graph? Is a tree? Right? No, it's not tree. Why? Because they're not connected. So tree must be connected. So they have a what? Two parts, right? This part and this part, right? They're not connected. So on the tree must be connected graph. So we had definition before regarding for tree, but let's bring the definition of a tree in the graph. Okay, what type of graph is a tree? Okay, so tree is a connected acyclic unidirectional graph. Okay, so this is the definition of the tree in the graph. Okay, so we defined okay whether this graph is a tree or not. We need to first look at what? Whether they are connected. Okay. Second, whether they have a circle or not, right? If they have a circle, it's not a tree. Okay, so tree must be capable non-circle, right? And then whether they have a direction or not, right? So this is undirected. So these three characters. Okay, so it's regarding for the trees. Okay. So now let's look at the relationship between the vertex or node and edge in the tree, okay, and the graph. For example, let's look at this. Okay, so if a tree has n vertex, for example, how many vertices it have? 1, 2, 3, 4, 5, 6, 7, right? 7 vertex, right? So how many edges it should have if this is a tree? How many edges? We discussed about the regarding for the impulse lecture, right? We talk about tree. We know the what? We know the nodes of the tree and how many edge on the inside the tree. Should be n minus 1. Okay. So there's a relationship between the vertex and the edge. If this is a tree, so it must be what? If you have n vertex, they only have n minus 1 edge. If this is a tree, okay. So in this case, it will be 1, 2, 3, 4, 5, 6. Okay, six edges. If less than n minus 1 edge, okay. If less than, let's make case. So if less, for example, less than 6, we break 1. Okay. So this is what? It's not become a tree because what? It's disconnected. It's not connected. Okay. Again, if more than 1, more than 6. In this case, more than 6, right? More than n minus 1 edges. For example, add any edge, right, between the two vertex. This is what? It's also not tree because they have what? They have a circle, right? So there's at least one circle if more than n minus 1 edges. Okay, for the tree, the number of vertex and edge is what? So when you have n vertex, they must have n minus 1 edge if it's a tree. Okay, spanning tree, right? Spanning tree. What is spanning tree? So it's a connect undirected graph with n vertex. Okay, if there's a graph, they are connected, and undirect is connected undirect graph with n vertex. So the goal, we want to find the subgraph. Okay, the subgraph maintain what? Keep all the vertex. Okay, second, they have the n-1 edge. Okay, n-1 edges. And the subgraph is connected. Okay, so if there's a graph, you want to find the subgraph contain these three characters. It means this subgraph is a spanning tree. Okay? For example, this is a graph, right? They define the weights, okay? They have each of the paths have weights, right? They are undirected, right? And connected. We need to keep all the vertex, right? How many vertex? It's 7, right? 1, 2, 3, 4, 5, 6, 7. 7 vertex, right? And we want to keep what? 6 edges. And within these 6 edges, they can connect to all the vertex. All right, okay? So now we want to find the what? So we want to find this subgraph because this is a spanning tree, okay? Okay, and for example, we can get this one, right? This we just saw that, right? The example, right? We keep this one, this one, this one, this one, this one, this one, right? 6 edges, 7 vertex, and they all connected within unidirectional graph. So this subgraph is a spanning tree. Okay, so what's the weight? What's the total weight? Sum up together, right? 2 plus 4 plus 2 plus 7 plus 5 plus 1, which is 21. Okay, the weight is 21. Okay, all right. Is it only one spanning tree in the graph? No, have more than one, right? Of course, more than one. For example, we can get this one, right? Like a star, right? So this is what? This is a 7 vertex and 6, sum minus 1, 6 edges. All the vertex able to connect it within the 6 edges, right? So this is also the spanning tree. So in this case, the sum of the weight equal to what? 25. Just add them together, 1 plus 3 plus 7 plus 4 plus 8 plus 10, plus 2, right? What about this one? This is also the what? Spanning tree. Okay? So we have a 7 vertex, okay? 7 vertex, and then what? How many edges? 6 edges, right? And all the vertex able to connect it with each other, right? Always can find a path within these 6 edges, right? So this is spanning tree. The sum of weight is 26 in this case. Okay, what about this one? This one also what? Also the spanning tree. Okay. So this total weight, sum of weight is what? 16. 16. Okay. So here though, we a lot of scenario. Okay. So we want to find what? We want to compare within the weight, right? Even though we know, oh, this is a spanning tree, we can visualize. Okay, can find a spanning tree, right? Give you a graph, right? But we want to find what? Minimum weight of the spanning tree. Okay. So there's a definition for that. We call the minimum spanning tree. Definition: a spanning tree have the minimize the sum of the weight. So this type of the spanning tree we call the minimum spanning tree. Also use MST. Okay. So this one is a minimum spanning tree because the sum of weight is minimum. We saw the several examples, but this is the smallest weight, right? Total weight. Okay, so that's how we can get from a minimum spanning tree. Okay. Any question before this definition? How we can get this minimum spanning tree? Pretty straightforward, right? Okay. Okay, how we can use it? How we can use the minimum spanning tree? Just give you example here. Like a muddy city problem, right? Muddy city problem. I think it's a typical problem we see in our real life. So the city have the muddy road, okay? The mayor want to pave the road, okay? Want to pave the road. Okay, now there's a requirement or constraint here. So First, they have enough road must be paved so that everyone can travel from his own house to anyone else's house. Second, the pave should be cost as less as possible or as little as possible. So that's a typical application we need to use in the minimum spanning tree. Okay, make sense? For example, for each of the pave, right? For each of pave, for each of a house, we can treat as a vertex. Okay, each of the road, okay, the muddy road, we call that is edge. So in that case, we want to find what? Minimum spanning tree. So first, all the house able to connect it. Second, the total weight is minimum, right? So in this case, it's what? So this kind of can satisfy this constraint. Okay, that's the simplest example we use in our real life. Okay. So for example, we can get this pave this way, right? So we can connect each of a house. Also, we have to calculate, okay, or estimate how much going to cost per kilometers, right? From the muddy road, pave the muddy road, and then we can do the calculation regarding for the how to find the minimum spanning tree, make a plan. Okay, good though. All right, so we know the minimum spanning tree, and we know it's useful, right? And we're able to use it in our daily life. And then we need to think how to find the minimum spanning tree in the graph. How to find out the code. Okay, we need to create the algorithm, right? We need to create the algorithm how to find the minimum spanning tree. Also the total weight. Okay. Okay. First, let's discuss about this algorithm, right? Called Prim's algorithm. So Prim's algorithm is a typical way to find the minimum spanning tree. So they're using what? A very greedy approach. Okay, greedy approach. So the basic idea is what they do here is grow the tree in the successive stage. Okay? What I mean here? So the steps is first, initially, we find one vertex, okay, any vertex in this graph, no edge, just find any vertex. And then we start a loop or iteration, right? So we add the vertex and find the minimum weight of the minimum weight edge into the tree, okay? And then through what? Through this iteration, we must maintain the property of the spanning tree in the graph. First must be connected. Second must be non-circle. And then we run how many times? Run the number of the vertex iteration and jump out of the loop. Okay, so this is a very arbitrary thinking, right? So we want to find first we choose any vertex, and then we find this all the paths related to this vertex, and then find the minimum weight, and then add into the set. That's how they're thinking regarding for Prim algorithm, right? Okay, let's look at this example. The same example, we have a different weight for each of the edge, right? Okay, let's set up the site U to store the vertex of the spanning tree. Okay. We have the iteration one. Pick any vertex in the graph. For example, we pick B. Okay, pick B. This one. Okay. Now, how many edge? Now we can directly add B into this site. Okay. Now we want to find what? In the iteration 2, we want to find the edge connecting to B, right? Connecting to this to this vertex. What edge connect to B? We have what? We have the BE, right? BD and BA. Okay? BE, BD, and BA. And then we want to find the minimum weight. Minimum weight with what? BD, because it's 1, right? This is BE is 2, BA is 4. Okay, so BD is smallest, right? So, and then we need to do what? Because BD is smallest weight, so then we add D into the site, okay? So now the site is what? B and D, okay? All right, okay? Then let's continue with the iteration, right? Iteration 3. We need to find the edge connecting to the B and D, okay? So B and D connect into the set of U to other vertex, right? Okay, so in this case, what being connected to the B and D? We have what? BE, right? And BA, right? So BE and BA, that's it for B, right? And then regarding for D is what? DE, right? DG, DF, DC, DA. Okay, so this edge connect into the B and D. Okay, make sense? So among this edge, which is the smallest? Among this edge, which is smallest? BE is smallest, right? BE is smallest because it's 2, right? All others is more than 2, right? And then we need to add what? Add E, right? E into the site U. Okay, add E. And then we keep going. Do you remember? Can you see this? We have 2 paths here, 2 edges, right? Connecting to B to E and B to D. Okay? Yeah.
For that last one, B to E was 2, but also D to A was 2.
Yeah, we just found the random. Good catch. Yeah. Okay. Okay. Like the iteration 4, we find an edge connecting to where? B, D, E to other vertex. Okay. B, D, E to other vertex. Okay. What they are? We have what? BA. That's it, right? For BA, right? We have this side connecting to this side. Okay. We have a BA, and then we have what? DA. Okay. And then DC, and then DF, and DG, right? And then for E, what do we have? EG. That's it, right? Okay. We only can find this path, right? This path. Okay, on the red mark. Which is smallest? DA is smallest. Okay? Yeah. So, yeah. Back to your question. Okay, and what do we do? We add A into a site. Now, add A into a site. All right? Okay? Keep going. All right? Iteration 5. What do we have so far? We have the B, E, okay, B, D, E, A, okay? We have this one. We want to find what? We want to find the edges connecting to the B, D, E, A, and this vertex, right? Okay, what do we have? We have what? E, G, right? And then, that's it, right? For E, that's it, right? D, G, D, F, D, C. Anything else? Anything for B? Nothing for B, right? Okay. And then we have one more for A, right? A, C. Okay, so this edge being connected is 2 sets. Okay, which is smallest? DF, right? It's already here. DF is smallest. We have 4, right? All others greater than 4. And then what do we do here? Add F into a site. Okay? So we can see this path, okay, this edge is being chosen, right, to build up the spanning tree cumulatively. Make sense? Okay. Keep going. Iteration 6. So far, what do you have so far? The U. B, D, E, A, F. Okay? B, D, E, A, F. Okay? We need to find the edges connecting to this set of U, right? B, D, E, A, F to other vertex. So we have this side, okay, connect to C and G, this side. Okay? All right? Okay. We have so far. What do we have so far? We have what? AC, right? And then anything for B? No, right? Okay. And then we have what? DC, right? Anything else? Yeah, DG, right? DG. Okay. And then we have what? FC. What else we have? FG. And then EG, right? So we have this number, red color, this number being what? Being a count, right? In this connection, in this age. Which is smallest? C, right? Okay, CF, right? Okay, you can find the FC is smallest. It's what? It's a 1, right? Then what we do? Add C into the U, into site. Okay, iteration 7. What do we have so far? What do we have so far? Find the age connecting to the B, D, E, F, E, A, F. Oh, it's down, right? Okay, 7. Okay, sorry. B, D, E, A, F, C, right? B, D, E, A, F, C. This one connecting to the what? This vertex. Only one left, right? What's being connected? We have EG, right? DG, and FG. That's it, right? Which is smallest? This one, right? So the FG have the smallest weight. Okay. What do we do? Add a G into the U, into a site. Okay. Now we, how many times? Number of vertex, 7. Okay, we're done. Okay, now we find what? We find the. Now we have all the vertex have been added to U, right? And we can return this tree, right? And total weight. Okay, so now this is what? Minimum spanning tree. This is the last example we just see. Okay? Clear regarding for this algorithm? Okay, good luck. Okay, some pseudocode. Okay, so what we use, what we need to leverage for this kind of algorithm? We always find what? Minimum weight. Okay, we always need a minimum, which kind of, what type of the data structure we learned before can leverage with heap, right? Heap, minimum heap, right? Or priority queue. Okay, that's how it works here. We initialize the minimum span tree site with one starting vertex, any vertex, okay? Create the minimum heap, okay, or priority queue of the edge connecting into the minimum spanning tree, this site. And then we process a while loop, okay? So if the condition minimum spanning tree is not including all the vertex, we'll be keep looping, right? Keep looping. So we first pick the edge with the smallest weight from the heap. If the edge connect to the vertex, not in the current minimum spanning tree, not in this site, add the vertex to the minimum spanning tree. Okay. And then we add all the edge from this vertex to this heap. We need how to do to restructure the heap. Make sense? Okay. Repeat until all the vertex are including this minimum spanning tree. Okay, that's how we implement by the code. Okay. This is the code on Python. Okay, C++ is very complicated, so I just use Python. Okay, so Python pretty straightforward. Just from the what? From pseudocode, you can make, right? Okay. By the way, can you guess what the time complexity? Can you guess? We're using heap. What? N is what? Number of what? Is edge or vertex? What's n? Now on the graph have two. One is vertex, one is edge, right? Yeah. So it's log n, right? Because when we do the operation insert deletion regarding for heap, it's log what? Log vertex, right? And then how many edges? Okay, yeah, so it's what? H times log n, log v. Or E times log, okay, E, edges times log E, okay? So because spanning tree and the vertex, they have the relationship, right? Okay, but it's not required for this course. Just you guys to know about that. Okay, how to can get that. But this if you want to prove as mathematically is a little bit complicated. Not required. Okay. All right. This is one way, right? Is there any other way? Okay. Let's introduce second argument to find spanning tree. Okay, minimum spanning tree. They call the Krusak algorithm, right? Krusak algorithm. Okay, so this algorithm just tell you a step. Okay, tell you a step. They first to sort all the edges in the non-decreasing order of their based on the weights. Okay. Second, initialize the MST, minimum spanning tree, as empty site. Use a disjoint site union, DSU. We didn't learn this, okay? We didn't learn this structure, but you can ignore that. Which is in this algorithm, we just introduce what the algorithm is. We don't apply the code, okay? So on final exam, I won't ask you about this code, but you guys, it's good to know, okay? Good to know this algorithm. Or unified the data structure to tracking the connecting component, okay? They use this to track the component. And then we do what? For each of edge, right? Starting and end in the sorted list. If the starting vertex U and V belong to a different component, add edge into the MST site, and unionize the site. If U and V are already connected on the same side, skip edge to avoid this circle. So it will be stopped when the MST have the V minus 1 edge. Okay, V is also number of the vertex. Okay, so this is N minus 1 edge. Okay, so it means first it count by what? Vertex. This is based on count by the what? Edge. Okay, to loop based on the edge. Okay, let's look at this same example. Instead, we use the ABCD. We convert into the what? The numerical value for that. It's easier to describe. Okay, for example, here we have the V1, right, for the vertex B, V2 for vertex E. Okay, so V3 for vertex A, V6 for vertex C. Okay. Okay, V4 for vertex D, V5 for vertex G, and V7 for vertex F. Okay. First, we build a queue of the edge. Okay. Sort the elements so that the weight are in the ascending order. So it's a non-decreasing order. Because why? Because there's some duplication. Okay. So that's why. Non-decreasing order. So we find the edge, right? For example, the edge 1 to 4 have the weight is 1, okay? And what? We have the 6 and 7. We have weight is 1. This is the smallest. And then we have 1 and 2. This weight is 2, right? 3 and 4. 3 and 4. Weight is 2, okay? And so on, okay? So we find their age, all the age, and based on the weight for the sorting, process sorting, insert into the queue. Okay? We create the site, okay? Tree site to record all the selected edges. Okay? Okay, it's an empty site. Now let's start. Okay, let's start how that works. Iteration 1, we perform the DQ. Okay, and get the age, right? 1 and 4. Okay. So this is the 1 and 4, right? Okay. 1 and 4 are not inside the same tree, right? So there's no path between 1 and 4. Okay. So we accepted the age 1, 4 and appended or insert 1, 4 into this site. Okay, we insert the what? Insert the edge. Okay, directly insert edge 1, 4. So now we pump the 1 to 4, right, on the Q, right? And then what we do? Iteration 2 is what? We find DQ, right? DQ this edge, 6 and 7. 6 and 7, where's 6 and 7? 6 and 7, right? 6 and 7. So perform the DQ and get the edge of 6 and 7. 6, vertex 6 and 7 are not in the same tree, okay? 6 and 7, there's no path can link into 6 and 7, right? Okay? And then we accept this edge and then add our appendant 6, 7 into the site. Okay? Now we keep going. Okay, keep going. And then we continue perform what? DQ. Okay. DQ we got what? 1 and 2. 1 and 2, right? Okay. 1 and 2. So what do we hear? Between this this one B and E, right? 1 and 2, is there any path can link between these two nodes? No, that's not within a tree, right? So they're not in the same tree. So we accept this edge, okay, between 1 and 2, and then appendant into the site T, okay, 1, 2. Okay, keep going. Okay, keep going. Now we find the edge 3 and 4, right? 3 and 4, okay, 3 and 4. It's a 3. V3 and V4 are in the same tree or not? It's still not in the same tree because there's no path between the V3 and V4. Okay? So we accept the edge 3 and 4 and also appended 3 and 4 into the site. Okay? Now we keep going, right? We keep going. DQ, okay, the edge 2 and 4, okay. Edge 2 and 4, where's 2 and 4? This 2 and 4, right? Is this 2 and 4, is this V2 and V4 are in the same tree or not? Yes or no? Yeah. Why? Because we can't find the path linked up into the V2 and V4 or D and V1 because we have path there. Okay? All right. We have a path inside this tree. You can find. You can go through from B to D to E or V4 to V2. Okay. So in that case, that's in the same tree. Okay. What do we do? Reject this edge. We don't need to add this edge inside this T site. Why? Why we reject if there's a path there? Yeah, it will become a cycle. If we add this in, okay, add this in, becomes a cycle, right? I will have a cycle. So this is not will be not what the spanning tree, okay? Not tree, okay? So that's why we reject it. Keep going, right? 1, 3, right? What's 1 and 3? This one, right? Okay, so 1 and 3 are in the same tree. Yeah, yeah, it's in the same tree because V1 and V4 and V3, they are connected, right? So V1 and V3 are in the same tree. Just rejected. Now we DQ the what? Edge 4 and 7, right? 4 and 7. 4 and 7. Is 4 and 7 are in the same tree? No, right? No, are not in the same tree. So we can accept it for edge 4 and 7 and appendant, or you can insert 4 and 7 into the T site. Okay? Keep going. We DQ the edge 3, 6. Okay, 3, 6. It's a 3, 6 are in the same tree? Yeah or not? Why? What? Yeah, these are in the same tree, right? Okay, so therefore we reject 3 and 6, right? Okay, keep going. 5, 7. V5, 7, right? V5 and V7, this one. Okay, we DQ the age 5 and 7. So is this V5 and V7 the same tree? It's not the same tree, right? Not same tree. We have to, well, we accept the age 5, V5 and V7, and then append this age into the set T. Okay, so how many now? How many number of the age? 6, right? So we have six age. So it's a match what we require because they have 7 vertex. So just need the 6 edges, right? So if the number of age is equal to the number of vertex minus 1, we can out of loop. This means all the vertex be found and connected. Okay, so we can ignore the rest of Q. So we can return the MST, this side, also the weight. Okay, so that's how this algorithm works. Okay, so that's it. That's it regarding for minimum spanning tree. We learned the 2 algorithms, right? Okay, one prime, one is a cross circle. Okay, cross circle algorithm to find the spanning tree into the graph. Okay, it's good though. Okay, we finished early. That's good. Okay, I will post the code in the on the D2L. You guys can, if you guys want to know, you guys can learn from that. Okay. All right. Okay. Thank you.